In this module, we will revisit Poisson regression through the help of an R dataset. The R dataset is the gala dataset, which is found in the faraway library in R, and it gives the number of varieties of tortoise on various islands of the Galapagos. As you know, this dataset has historical importance, and you can look at the work by Charles Darwin for more information on the tortoises and their abundance in Galapagos and what scientific information this gives us about evolution. We shall first consider modeling the dataset using linear regression, look at some of the diagnostics, and see that they indicate that linear regression is perhaps not appropriate. We shall next look at Poisson regression and see that the diagnostics from the standard Poisson regression are also not satisfactory and suggest that we should use some kind of variance. We shall finally look at over-dispersion as also various measures of goodness of fit for this dataset. Learning objectives for this module. We shall first introduce the gala dataset from the faraway library in R. Next, we will look at trying to build predictive relationships from this data, firstly using linear models. As the outcome for this dataset is a count, we shall next look at the fitting of generalized linear models and the associated diagnostics. And finally, we shall look more detailed at the presence of over-dispersion and get an independent estimate of the scale parameter. The gala dataset is included in the faraway library in R. The gala dataset has information on the number of species of tortoise found on each of 30 of the Galapagos islands, as well as the number that are endemic to this island. Along with information on the number of species of tortoise, we also have 5 covariates, which are 5 geographic features of each island. For more information on this dataset, you are referred to Johnson and Raven, 1973, and Weisberg, 2005. We shall first begin by fitting a linear model on the gala dataset. As I said, the data concerns the number of species of tortoise on the various Galapagos islands. There are 30 islands, and for each of the islands, we have measurements on 7 variables. These are species, which are the number of species of tortoise found on the island; endemics, which gives the number of endemic or native species to the island; elevation, the highest elevation of the island in meters; nearest, the distance from the nearest island in kilometers; a variable called S-cruise, which is the distance of the island from the Santa Cruz Island in kilometers; and adjacent, which is the area of the adjacent island in squared kilometers. As you know, the Galapagos Islands have been very informative for the theory of evolution, and for more information on the implications of this kind of data, you are requested to visit the link which has been mentioned on this page. We start by first reading the data into R. So we call the faraway library using the command library faraway, and we attach the gala dataset using attach gala. We can first run some summary statistics using summary, gala, names, gala, etc. to get a better sense of the data. To look at pairwise scatter plots of the variables, we can also look at the command pairs gala. You are encouraged to run these commands to get an idea about the results. To move on to multiple regression, let us first fit a linear regression to the data. So we use the lm command in R and run a linear model where the outcome is the number of species on 5 of the island characteristics: area, elevation, nearest, S-cruise, and adjacent. This is stored in the R object gfit. We can look at the results of this fit by typing summary gfit, and having done so, we can get the predicted values and the residuals using gfit$fit and gfit$res. We can also choose to fit various subsets of the covariates and to get a formal idea about the significance of each model, we can compare two nested models using the anova command. So say for example, we use the lm command to fit two models G1 and G2, where G1 includes the covariates area, elevation, nearest, S-cruise, and adjacent, and G2 includes area, elevation, nearest, and S-cruise, and omits adjacent. Then G2 is nested in G1 in the sense that G2 is a special case of G1 in the case when the coefficient of adjacent is 0, and we can compare the two models using ANOVA of G2 and G1. Similarly, we might want to test whether the coefficients for the variables area and adjacent are equal. To do so, we fit G1 as before, that is G1 is a linear model of species on area, elevation, nearest, S-cruise, and adjacent, and G2 is a similar linear model except that one of the variables for this model is now I of area plus adjacent. This forces the coefficients of these two variables to be equal. Now again, because we have nested models, we can use ANOVA of G2 and G1 to get the corresponding significance values. We may want to test whether the coefficient of area can be set to a particular value, say for example -0.1. We can then fit the model as before, except that the term for area is now specified as an offset, which tells R that there is no coefficient corresponding to this term. So offset of -0.1 star area means that the linear regression should be fit by assuming that the coefficient of area is 0.1. Similarly, as before, we can use the ANOVA command to test for the significance of this model. We can get confidence intervals for the regression parameters. This can be done in various ways. Firstly, we can extract the coefficients using summary $coefficients. This will give us not just the regression coefficients, but the standard errors, the t and the p values in the form of a matrix. We extract the first two columns, so beta is summary G1 $coefficients, the first row, which is the estimated coefficients, and SE.beta is summary of G1 $coefficients, the second column, which is the standard errors. To get the confidence intervals, we need to get the critical value of t, and we can do this using the qt command with degrees of freedom equal to G1 $df.residual. The individual confidence intervals can then be constructed as ci.beta as beta plus minus T95 star SE dot beta. Note that it is also possible to get the confidence intervals by running the conf-int option on the G1 object. So here we are fitting a linear model again to the data. We are to look at some of the diagnostics. The variable endemic is not of interest to us, so we begin by calling data gala and by dropping the second column of the gala data set. We then fit a regression of species on all other variables except gala, and we ask R to fit the residuals from this data set. So plot predict L mod residuals L mod will give us a plot of the fitted values against the residuals. So we look at this plot, which is given on the left panel of the figure, and we can see that the plot is somewhat funnel shaped. This, as you know, is evidence that we have non-constant variances. Now, when we have non-constant variances, the obvious option is to try some variance stabilizing transformation. So common transformations for the case where we have counts are the log transformation and the square root transformation. If you wish to get a more subjective method of If you wish to get a more objective method of determining the appropriate transformation, you can also use Box-Cox transformations. So by using Box-Cox, it is possible to show that the appropriate transformation is the square root transformation, and we see a similar plot of residuals versus fitted for the linear model in terms of the square root transformation. We can see that the plot is no longer funnel shaped, and it appears that using the square root transformation has tackled the problem of non-constant variance. So here is the code which we used to produce the plot on the previous slide. So mod t is an object constructed using a linear model of square root of species on all the variables excluding endemic, and we plot predict mod t and residuals mod t to look at the variances. Here is the summary of mod t. As you can see, the multiple r squared is 0.783, which is a reasonably good fit considering that we have observational data. However, a problem with this model is that we have transformed the coefficients, and hence to interpret the coefficients as the effect of a unit change, we note that they give the effect of a unit change on the square root of counts, which has no ready interpretation. So to get a more satisfactory answer, we shall move next to Poisson regression. Poisson regression will assume that the counts for each of the islands, say yi for the ith island, follows a Poisson distribution with mean mu I. We shall assume the canonical link, which you know for the Poisson regression is the log link, and thus log mu I is equal to the linear predictor eta I equal to xi prime beta. Xi prime beta is constructed using the covariates of area, elevation, nearest, S-cruise, and adjacent, with beta giving the corresponding unknown regression coefficients. Estimation is possible by maximizing the log likelihood given by L beta equal to summation I1 to n yi xi prime beta minus exponential xi prime beta minus log yi factorial. The score equations are thus summation I1 to n yi minus exponential xi prime beta hat xj equal to 0 for all j equal to the number of covariates, in this case 5. To get a measure of goodness of fit, we can construct the deviance statistic, which we know is given by d equal to twice summation I1 to n yi log of yi by mu I hat minus yi minus mu I hat. The Poisson deviance statistic is also known as the G statistic in the literature. So we can fit the Poisson regression model using the GLM command in R. So mod P of GLM species on family, species on all the other covariates with family equal to Poisson will fit the canonical link, which is the log link. We can look at the results of the fit by using the summary command on the mod P object. The measure of goodness of fit is given by the residual deviance and we can compare this by comparing the deviance of the model against the average value of a chi-square distribution with degrees of freedom equal to that of the model. Just as we have compared various nested models in the case of linear regression, we can compare nested models by taking the difference of the deviances and comparing this to the chi-square distribution with corresponding differences of degrees of freedom. We can also test for the significance of individual predictors and construct confidence intervals for beta hat. Note that this has already been done in terms of the z values and the p values. These correspond to the walled tests of the corresponding regression parameters. Similarly, we could also ask R to give us the results of the likelihood ratio test or the score test. Note that the residual deviance is about 717 on 24 degrees of freedom, and this, however, indicates that the model is not a very good fit. We next check the residuals to see if this large deviance is perhaps due to an outlier. This can be done by constructing a half-normal plot of the residuals, as has been shown in this figure. Note that if we say residuals of mod P, then by default R will use the score residuals from the Poisson regression. However, the half-normal plot of the residuals indicates that there are no notable outliers, and it could be that the structural form of the model is not quite correct. However, if you look at different choices of the link function, you will see that the proportion of deviance remains more or less the same, and it is quite difficult to construct a model which explains a better percentage of the variance. You can look at the proportion of deviance explained by this model, which is 79.6% and about the same as the R square reported from the linear model. A key assumption of Poisson regression is that the mean is equal to the variance. Let us see if this holds for this data set. It is difficult to estimate the variance for a given value of the mean, but we can use y minus mu hat square as a crude approximation. We plot this as a crude estimate of the variance against the mean, and This has been shown in the left panel of the previous slide. You can see from this plot that the variance is proportional to but larger than the mean. So it appears that a reasonable assumption for the data is that the variance is equal to some constant phi times the mean. We next would wish to get an estimate of phi, and this can be done as phi hat equal to chi squared divided by n minus p, where chi squared denotes the Poissonian sum of residuals. So we construct this using dp as sum of residuals mod p type equal to Poisson squared by mod p dollar df dot residual. This gives us a scale parameter of 31.74 as opposed to the standard assumption that the scale parameter for the Poisson distribution is 1. We can next update the regression coefficients using the dispersion equal to the scale parameter which we have just constructed. An alternative could have been to fit quasi-Poisson regression. Note from this slide that the coefficients do not really change. However, there is a difference in the standard errors and hence in the z values and the corresponding significances. Finally, model selection. When we compare the Poisson model with over-dispersion, we should use an f-test rather than a chi-square test. As in normal linear models, the variance in this case needs to be estimated, and hence we require the use of the f-test. The f-statistic from the summary are less reliable, and so the f-test is performed. In this example, however, there is little difference between the two. In this module, we have considered a case study based on modeling of the gala dataset from the faraway library in R. This looks at tortoise abundance on various islands of the Galapagos. We have first fitted standard linear regression to the data and seen that the diagnostics indicate that linear regression fitted on the outcome is perhaps not adequate. Box-Cox transformations are possible, and we have used the square root transformation, which we know is the natural transformation to use in the case where we have counts. We have also fitted a Poisson regression, looked at the model fit and the diagnostics, and seen that we have some evidence of over-dispersion. Finally, we have modeled this using the quasi-Poisson family in R.